Okay, welcome to the first class meeting of EC202, Introduction to Probability and Random Processes. So usually in the first class meeting, I talk about the syllabus and just have fun with students, but I've changed my mind. So I'm going to start our course. So the first topic is why this course, the probability and random processes, is essential in the electrical engineering curriculum. And then I will talk briefly about the probability theory you are going to study throughout this course. And then I will also talk about some related courses. So sorry about that. I will talk about the preview of what you will learn in this course. And then I will just talk about how to succeed in this course and other things. So about the syllabus, you read it. It is posted on the PLMS. You carefully read it. And if you have any questions, ask me after the class meeting or before next class meeting, after next class meeting, until we settle down the final version. Okay? So this is the first page. What is this one, by the way? Probably some of you have seen this one because I'm using this picture again and again and again for last 7 or 8 years. And this is kind of a modified version of the Petronas Twin Tower in Malaysia. So we have 2 big towers. And of course, in reality, there is only one bridge here. And at that time, I used the PC Paint to copy and paste a lot of bridges. So why this funny picture appearing on the first page? Because as many of you have not yet get the idea, electrical engineering is largely divided into 2 buildings. So just for simplicity, let me say left building and right building. Got it? There are 2 buildings. And what you are currently is probably you are in front of the building, and which building to go you haven't yet decided. And I personally reside on the right side of the building. And what is the task of the persons in the right side of the building? They think about what would be the logical and mathematical functions would be beneficial for human being. So we usually model the electrical system using mathematics and derive what is optimal, what would be good, something like that. On the other hand, the persons on the left side building realizes that idea by really implementing the systems. Some people just focus on a single transistor. Some people focus on the collection of transistors. Some people just ignore all of them. They believe, okay, some people on this building have the chip, and I will put those chips to build some other things, something like that. So on the left side building, you start from, for example, chemistry or physics, like quantum physics, or sometimes thermodynamic mechanical statistics, something like that, to model electrical components. So I found that some of you are in sophomore or even the senior level, and you may have now some ideas like this. For example, if you take signal gen systems, probably professor on the right side building teaches you. If you take electromagnetics, it is highly likely professor on the left side building teaches you. If you take some semiconductor devices, left side building professor teaches you, and they talk about diffusion and Einstein's contribution other than relativity, and you have surprise, right? And if you take signal processing, communications, they always talk about a lot of mathematics. Exponential function with power, complex value, something like that. Got it? So we have, largely speaking, two different buildings we have. Of course, you never noticed, but there is a huge, much bigger building, not yet pictured here, is behind these two buildings. That is actually computer science and engineering. Initially, computer science and engineering never came out from electrical engineering at the first stage of electrical engineering. But now, as many of you already know, computer science and engineering has become a huge area. And if you really want to study that, then you go to that department and take courses. But some of the people love electrical engineering who builds, for example, computers, not use computers. In that case, you need these people living in this twin tower. Now, so you know that there are two buildings, but why probability? Probability theory is taught because in both buildings, we have to confront uncertainties. What is uncertainty? That is not certain. Then what is certain? Sometimes we say it's something deterministic, something perfectly known. Then uncertainty means that something is not perfectly known. Then what happens? We have many problems. As high school students, long years ago now, you've learned some topics like this one. There is classical deterministic system like F equals ma and some other equations, E equals mc squared. You have beautiful equality. Some physical quantity equals some other quantities combination. The problem is that you also know that even though there is certainty, we have some problem like chaotic systems. The system is perfectly deterministic, but you can never predict after y. There is another thing like this one. You have, for example, linear differential equation. But depending on the slight change of initial condition, you may have totally different solution. You've already know that, right? And what else do we have? We have statistical mechanics. And you may say that, oh, statistical mechanics, why that comes in electrical engineering? I kind of avoided that by not to choosing chemical engineering or physics. And I fled from those departments. And why he talks about that? Because, let me amplify this page. So you know the famous Ohm's law that can be written as V equals I times R, or I equals V over R. What does that mean? Your current as a function of time is constant if you are given a constant voltage source and a resistor. You all know that. You've been taught that from your elementary school science class, right? Everybody just believes that I equals V over R. So this is a constant function. And you may say that Ohm's law is about deterministic, some certain situation. But actually, that is totally a lie. Of course, it's a white lie, not some other lie. The problem is that, as you will learn in this course, not seriously, but in other courses, probably, every resistor is better modeled as an ideal resistor followed by a noise source or another voltage source. What does that mean? Your current here, which is constant, actually equals your applied voltage plus this some noise voltage source divided by R. What does that mean? If you really observe the current here, it's not constant. Then can you perfectly predict what will happen before you apply your voltage source? Unfortunately, it is impossible. Because as we will learn in this course, this V sub n of t is so-called a random process. Here, the term process confuses you. In that case, just replace it with random signal. So it's some signal that has uncertainty. So you have current that is also uncertain. Why this happens? Because in the resistor, there are many electrons. And the resistor has some temperature. And what happens? What does that mean by the resistor temperature capital T? Anybody? Probably you've learned about ideal gas physics. At that time, some of you had the idea that even though we claim in this cube there is an ideal gas with ideal molecules, these molecules have what? Different kinetic energy. And temperature is mere an average of this kinetic energy. What does that mean? Even though we claim that the electrons have temperature 273 K, what does that mean? On average, they have that kinetic energy, but some of them has much lower energy and some of them has much larger energy. Actually, that is why even though your water on your mug cup evaporates, even though its temperature is much lower than 100 degrees Celsius. Some of them, some of the molecules may achieve that 100 degrees Celsius and evaporate. So we have a lot of electrons, not gas molecules because we are electrical engineers. We have a lot of electrons. What does that mean? We have to rely on, precisely speaking, statistical mechanics to analyze what really happens in our circuit. And of course, as you all know, the next thing is the quantum mechanics. Since our electronic device becomes smaller and smaller, now we can no longer ignore this quantum mechanical effect. And what does this Schrödinger equation mean? Even though the equation itself is deterministic, there is nothing random, no random signal at all. But this equation itself describes what? Describes time-varying probability density function of the position of electron. So even though this differential equation is deterministic, its solution gives you probability density function. Of course, some of you already know, as you learned in high school math, 확률 밀도 함수. So this probability density function gives you uncertainty. You don't know where is the electron. Okay? So uncertainty is always there. Finally, and I believe most importantly, this era is the information era. So information and telecommunication era, what does that mean? You want to transmit, you want to receive information from other sources and to other destinations. Why do you transmit information and receive information? Because there is uncertainty in information. You don't know what kind of final exam problem will appear on your EC 202 this semester. So that's why you come to this class meeting. Hey, let's see what kind of problem he would write on the final exam, right? And whenever we have this information imbalance, what do? We model that amount of information imbalance using probability theory. So as you already know that Isaac Newton tried to describe the kind of mechanical theory of the world using mathematics, Claude Shannon, who is called the father of information theory, tried to describe this information transmission and reception and compression and everything using probability theory mathematically. Now, I believe I emphasized enough why the handling, having this course important. Because in either building you are going to reside in the future, right side building or left side building, most of you will have to know how to handle uncertainty in the electrical system. Of course, there are some exceptions. For example, if you do some research experience in some lab in our electrical department, then if you ask your senior graduates, do we need probability theory? I've never seen since I took EC 202, something like that. Of course, there are some area where this uncertainty is not that important. But most of the labs, they will say that, hey, it's important. Especially if you want to study communications, everything is modeled probabilistically. Signal processing, financial signal processing. For example, you want to invest on the Bitcoin and you have no knowledge about the probability theory, you are destined to bankrupt. And other things. Then, whenever you have uncertainty, what are you going to do? Why it disappears? It disappeared. Okay. First thing is that naively, we just use inequalities. So we assume that there is uncertainty, and that uncertainty is a maximum that number, minimum that number. In that case, we have inequalities, and we want to handle this uncertainty. That would work, actually, in many cases. But it's very important. Even though I'm teaching probability theory, sometimes simple upper and lower bounding the uncertainty is much better. And you will find yourself, if you invest your lifetime salary on stock market. Okay, anyway. But this course not just talks about deterministic inequalities. That's kind of, we believe, easy and you can do it yourself. In this course, we are going to use and teach and use probability theory to handle uncertainties. And interestingly, this probability theory also will give you a lot of inequalities. Now, these inequalities rely on the existence of the mean value, existence of the variance. But whenever these things exist, we have much better inequality than some deterministic inequalities which do not rely on probability theory. So you will see many things. And even though I will not talk about this one, but it's also very important to mention how to generate pseudo-random sequences. Many of you already have used generative models in machine learning. And what happens? Even though you feed the same input, the outputs are different. Why do we have that phenomenon? Because this AI model itself has pseudo-random number generator. And these pseudo-random numbers contributes to generate different, sometimes hugely, sometimes slightly different outputs. And In order to generate pseudo-random number, here pseudo is translated as 의사. It's not doctor, something not genuine, something like that. So this pseudo-random number is not mathematically random, but very, very important in modern electrical engineering. For example, my major is communications, and I need to simulate numerically generating a lot of bits, sometimes noise also. Then what do? I probably use MATLAB, and MATLAB has the command rand, and what does it do? It generates pseudo-random numbers. And interesting thing is that you may believe that this pseudo-random number can be generated using nonlinear recursion like this one. Probably you've seen this, right? This equation, you know, right? Chaotic something. But actually, linear equation can also generate very pseudo-random sequence. Take a look at this one. This recursion formula is very simple and it's linear. This x sub something is either 0 or 1. Now, you need the memory size of 10. And for example, you run this equation, recursion formula, with initial state all ones. Then interestingly, you have very random number like 0 and 1 bits. And of course, since this is deterministic and there is no nonlinearity, actually it generates a periodic sequence. But this simple equation generates sequence with period 1023. You do it yourself if you have time. And especially this sequence is called M sequence. And it has application in GPS, the United States GNSS, and also previous CDMA systems relied on M sequences. Unfortunately, I'm not going to teach how to design this pseudo-random number generator, but I will talk about how to use pseudo-random number generators to generate some arbitrary random variable with desired distribution, something like that. Now, some of you may have interest in what kind of other higher grade courses are related to this EC202. By the way, formerly this course was EC302 and offered to the third grade electrical engineering students, but the department changed it and shifted it down to the sophomore level. One of the reasons is that professors in AI and machine learning professors wanted to expose you the statistical inference as early as possible. So that is one of the reasons. The problem is that many of you haven't yet taken any electrical engineering courses. No signal gen systems, no circuits. So I'm kind of actually feel very challenged this semester, even though I taught this course more than several times in the early years, or for juniors. Anyway, so here goes the courses: communications and networking. You need probability theory. AI and machine learning, you definitely need probability theory. Of course, we don't have any faculty members. Financial signal processing. We have a lot of professors in signal processing. Control and robotics also requires this knowledge. And devices and circuits, as I told you, this statistical mechanics and also quantum physics are very important. in these topics. So actually, you can hardly escape from dealing with uncertainties if you major in electrical engineering. Got it? Probably that's why you all have come to this course. Now, many of you may say that, hey, I learned probability theory when I was a high school student and middle school student, and even some of you elementary school student. And you may say that, is there anything I need to learn more? So in the remaining time of today, I will challenge you. So you try to find out, try to solve what I'm going to show soon, not on this page. Anyway, you all know that the probability theory is based on axioms. And when you, probably many of you, have taken the probability and statistics offered by the math department, you also have seen these axioms from your textbook in chapter 1. And usually you just flip over the page. Hey, I all know that A union B, A intersection. But what's the use of? You will regret that today. Anyway, so I will talk about this one throughout the course. And next thing is this one. What is probability? And also those chapter 1s talk about this relative frequentist perspective and the Bayesian perspective. I'm not going to spend many time today because many of you are not yet prepared to discuss this topic. But anyway, probability theory have now solid mathematical foundation thanks to Kolmogorov. And this probability theory, especially probability, can be differently interpreted. And depending on what kind of electrical system you are going to analyze, design, sometimes frequentist point of view is much better, and sometimes Bayesian interpretation of probability is much better. So you choose the right one at the right time, at the right place. Got it? Now, if you go to the graduate school, you will learn more about probability and random processes. Actually, electrical engineering department has the first year graduate level course called probability and random process. So only introduction to these two words are taken out. So we have probability and random processes introduction, and we have probability and random process not introduction in the graduate level. In addition to this graduate level probability and random process, we also study detection and estimation theory. That is second year graduate program. And if you have interest in machine learning and artificial intelligence, probably you will talk about classification, regression, and you will study those topics. And if you study optimal control, then you will study stochastic optimal decision theory later in probably graduate program. What is the common, most important thing you need to remember? Why do we study this mathematically? Because probability theory is a mere extension of logic, Boolean logic actually. Boolean logic has zeros and ones. 0 means false, 1 means true, and you have and or something implies implication. You know that, right? That logic theory is now generalized by allowing those numbers between 0 and 1. In logic, you have zeros and ones. In probability, you have numbers different from 0 and 1s, sometimes 0.5. By doing that, you perfectly generalize your logic. If you don't believe, you do it yourself in the throughout this semester. By generalizing the logic, which is the probability theory. What you want to do is we don't want to dispute about something. We want to have exact derivation and show that, hey, see this number. I'm right. You are wrong. We want to do that. Probably many of you have watched Saturday night debate. Some ruling party and opposing party members of the Congress come together and they talk about some topic. They just want to, how to say that, humiliate the other. Their objective is not to discuss, actually. And they just spend a lot of time. And after a while, the host of the show allows calling from the audience. So you dial the number and wait, and you talk about something ignored. We don't want to do that, especially or at least in engineering. We want to have some conclusion, undebatable result. So let's see this famous Montiel problem. And probably many of you already know this, right? Anybody who wants to describe this game? Nobody? Okay. So consider a quiz show. So, okay, consider a Squid Game, okay? Or for example, 1,000 people started from the beginning and only one person left. Got it? And you are the last one, and I'm the host. You are the guest. Got it? Now, I ask you, and saying that behind the 3 doors, only one door has the award. And if you choose other doors, you will. Got it? And now I ask you to choose which door. So which door? Number 1, 2, 3. Number 2, okay. Second door. And I know which door hides the award. And I just open one of the other 2 doors. For example, I open door 1, and there is no award. Now, I ask you again. So do you want to switch to door 3 or still want to remain in door 2? Okay. Why? Why? Why you want to stick to the first choice? Okay, so everybody understands what the situation is? Okay, then let's have a poll. So you have chosen door 2, and I have shown you door 1 does not have a prize. Now, raise your hand if you still want to stay in door 2. Only one? Okay, he also hesitates. Do you want to switch to door 3? Okay, how many? Okay, why? Why? Probability is twice. What probability? Why do you think so? This problem is so famous, right? So many of you have already exposed. Probably he was not exposed. But I still want to ask you, why? You say that, and you know that, probably you've read some popular science math book, the switching has higher probability to win the award. Why? And what kind of probability? Probability of what? Winning the car? Winning the award? By the way, the original problem has slightly different words, descriptions. So original problem is like this. Behind one door, there is BMW. Probably at that time, BMW was the most expensive and desired car. Probably in this time, probably Tesla. And the other 2 doors, goats. So if you eventually choose door 1, you get goats. No, actually, no. There is no award. Only BMW can be taken if you are correct. And I still remember when I first taught 302 long years ago to your long seniors. And I described this problem, how to solve and how to view this one. And after the class meeting, one of the students came to me, approached it to the podium and said that, Professor, I still don't need probability theory. I can just count the numbers and show that switching is better. And as one of you said that, has probability of winning twice than stick to the first choice. So show me, I said. And he just showed me how to find out all the cases in high school math, 경우의 수, so count, and then this number, so blah, blah, blah. So I said, you're right. So you may claim at that point, you don't need new theory or you don't need advanced theory. So this is my answer. That was the claim of the student. And I said that, can you generalize to the cases where you have L doors, M cars, N opened doors? And he said yes. And he used the same technique, ended up with the correct answer. So I have to devise another one. And he stopped to claim that he didn't need to study advanced course. So consider that. That show, not Squid Game, suppose this is a TV show, lasted for more than 10 years. And at the final stage, the guest confronts this choice problem. And you've watched 10 years of the game. Let's say that every week we have this show. A lot of games, right? And you have found that the host has tendency to hide BMW behind the first door, slightly larger, right? It's more than 1/3 ratio, right? You watched, for example, 1,000 this show, and you've found that BMW is hidden behind the first door, slightly larger than 1/3 of the older shows. But anyway, that's very important information, right? If you want to win the BMW. Another problem is that when the host has freedom to choose, when he opens, so situation is like this. Actually, BMW was hidden behind the second door. So I can open either first or third door. But if you watch and analyze all the 1,000 games, it seems I have a tendency to open left door more preferably whenever I have a freedom. Now you have those asymmetries, and then I ask, can you still just count all the cases and claim that your strategy is better? So actually, I put this problem in the graduate level probability and random processes course, and all the students failed to answer correctly. Now, in order to precisely calculate without any confusion, actually, you need these concepts even to solve this very simple Montiel problem. The first thing is that you need to have the concept of random experiment. But you already know that, right? 의사 실험, 모의 실험. random experiment, 모의 실험, trials, 시행, outcomes, 결과, event, 사건. You all know that, right? Whenever you took the probability theory course, high school, undergraduate, you've seen these things, and after 1 week, even professor didn't mention these terms. Just he gave you probability density function, how to calculate expectations. And you may say that, okay, that's just mathematical formalism, which I do not need to solve the real world problem. Actually, it is not. Probably many of you do not know what is this combined experiment and difference between independent combining and dependent combining of experiment. Even though you know the conditional probabilities, actually, he was half right. We want to have larger probability of winning the car. But we need something more, given or conditioned on the fact that we initially have chosen the second door and I have opened the first door. So we have to compute the conditional probability. Conditional probability of the BMW hidden behind the second car, given second door is chosen and first door is open, versus probability of BMW hidden behind the third door, given the same events, actually. So we need to compare these two conditional probabilities. And then you will find that if you switch, which means that the probability of BMW hidden behind the third door is twice the probability of BMW hidden behind the second door, both conditioned on second door is chosen, first door is open. So you have to compare precisely these two conditional probabilities. Of course, these two probabilities sum to 1. So you just want to compute only one of the conditional probabilities. And when we have perfect symmetry, like BMW can be hidden equally likely behind the 3 doors, the guest choose equally likely, host opens equally likely whenever I have choice, freedom, then you just need to count. However, if you have a slight asymmetry, or even when you have sometimes this generalization, many of you got confused. Okay, 3 door, 2, 1 is open, blah, blah, that's okay. But if there are L doors and M BMWs and N doors are opened, then you don't know the exact probability. Got it? That's why we need probability theory. Of course, you may say that, hey, this is just game show. As an electrical engineer, that may not be important. But actually, for example, Gemini or ChatGPT, whenever it generates some output, actually, it does what? So-called inference, right? These days, we talk a lot about 추론. That is actually the Korean translation of inference. What is inference? Actually, we do statistical inference, probabilistic inference, whenever we use machine learning models. And statistical inference is the core of why we learn probability theory, as you will see. Anyway, here goes by the way, homework 0. So you don't need to upload or you don't need to turn in. This is just to get the attention. So unlike my previous class courses, I'm not covering syllabus because that can be read by yourself. You can read syllabus. So you read the syllabus and bring your questions next time. especially paying attention to the midterm and final exam dates. It's fixed. I cannot change. We have too many students. So if your other course conflicts and those number of students are significant, that's vague, then I will reconsider changing the exam dates. But it's almost impossible to change the exam dates. So please pay attention to the dates and times for the midterm and final exam, and bring your question about syllabus. I will answer to those questions next time or today after the class meeting. Got it? By the way, many of you are just second year students, which means that you even haven't yet taken signals and systems. This course originally 302 had circuits theory part and signals and systems part. I'm going to try to much reduce those prerequisites, but it's impossible to completely remove. So if you are taking signals and systems this semester or circuits course this semester, it will greatly help when I talk about Fourier transforms or Laplace transforms or something like that. And after you take this course, as I told you, you can take communications and networking courses, signal processing, AI, control courses, and not undergraduate, but graduate level carrier transport theory, which is based on statistical mechanics. And also, if you are just taking this course, but in other departments like chemistry, physics, then you will feel much comfort when you study statistical mechanics or quantum physics. There are also advanced courses related to probability theory. And some of you still doubt, hey, AI, these days AI is so important, so this professor talks a lot about AI. But hey, let's see. So this is the book, very famous book, freely downloadable. The author just uploaded the free version, Mathematics for Machine Learning. And let's see the table of contents. First thing, introduction and what is this? Motivation. Second chapter is entitled Linear Algebra. Got it? So take it, take it. Analytic geometry, norms, inner products. Okay, you can say that it's part of linear algebra. Matrix decomposition, okay, still linear algebra. Here goes vector calculus. Hey, everybody have taken calculus, okay? Then here comes probability and distributions. And here comes optimization. And if you see other courses, they also talk about the mathematics for AI has linear algebra, probability theory. Here, you see, estimation and information theory, they are all related to the probability theory. And again, continuous optimization. So I'm not lying. I'm saying that this course is a foundation for your future courseworks. Now, we've spent around 15 minutes already and around have 25 minutes. So I will very quickly talk about the important topics we are going to study throughout this course. The first one is this one. I also still remember I was kind of dummified when I was taking this course. At that time, but when I was an undergraduate student, this course was for the juniors. The professor asked, probability of what? I tried to remember my high school knowledge, but I failed to answer that question. So today I want to fix the same confusion of you. Whenever we talk about probability, automatically with very high correlation, we have these words. Probability of event. Sometimes probability of the event that blah, blah, blah. probability of an event, blah, blah, probability of event, this event, that event. Anyway, whenever you have the word probability, then automatically you have of, and automatically you have event. So in Korean, whenever we talk about 확률, 사건의 확률, that is the kind of strongly correlated two words. The problem is that after we get familiarized, we know we talk about 사건의 확률. So sometimes we just drop. That confuses a lot sometimes. So whenever you have confusion, try to go back to this phrase. What kind of event I'm thinking about to compute its probability? Got it? So he said, actually, probability of winning the car. But translated it to what? Probability of BMW hidden behind the third door. Probability of event that host hid BMW behind the third door. Got it? So whenever you have confusion, try to make this event precise. Then you can remove a lot of confusion. And you will never say something like probability of X, something like that. Whatever X is. You must have some event. If X is not an event, this expression has no meaning. Okay? By the way, that piece of R means probability of something. Right? And in the second class meeting, this Wednesday's class meeting, I will talk most of these things. Random experiments, trial, outcome, event, probability of event. And then I will talk about the axiom, so probability space, sample space, event space, and probability measure. But I will try to avoid this measure theoretic probability terminologies. In the previous years, I talked a lot about sigma algebra of subsets, blah, blah, blah. But now this is for the second year students. So I'm going to decide, I have decided not to talk about measure theory. Anyway, if you have some discomfort after taking this course, take advanced courses. More based on measure theory. Then you will much have better clarity. Anyway, we will talk about statistical independence. This is different from linear independence, as you learned in linear algebra. That's different. The term independence is used in a lot of different subjects to mean different things. And we will talk about independent events. 3 key tools like conditional probability, total probability theorem, Bayes theorem. And then, as you already learned in high school and even in statistics, probability and statistics, we will talk about random variable. That is translated as 확률 변수. Then, here goes the interesting thing. We will talk about random vector. In electrical engineering, as many of you have already taken, we try to kind of define signal and system. Long before, when the time of Marconi or those pioneers in communications in early 20th centuries or late 19th centuries, at that time, there was no notion of signal and system. There was some physical something with wires and some spark gaps. But theorists kind of divided that one with signals and systems. And that actually revolutionized our understanding. So we try to view our electrical system like this one. We have something goes in and something goes out. And that idea, very simple, revolutionized electrical engineering. And now you are being taught signals and systems in the second year. Now, about the signals, what kind of mathematical entity do we use? To mathematically describe signals, electrical current, sometimes voltage, sometimes magnetic field, we use either scalar, real or complex, vector, sometimes matrix. What else do you want to say? Sequence of scalars, sometimes sequence of vectors, sequence of matrices. Sometimes we use a function, time function. Many times we call waveform. A time function of vectors. Sometimes field. Sometimes even polynomials. Sometimes graph. Almost every mathematical entities have been used to model electrical signals in electrical system. Unfortunately, in this course, we cannot cover all possible random something. So uncertainty, so signal with uncertainty, maybe a scalar with uncertainty, a vector with uncertainty, matrix with uncertainty, if you want tensor with uncertainty, sequence of scalars with uncertainty, sequence of vectors with uncertainty, blah, blah, blah. Too many. So fortunately, we are going to stop here. Got it? In this course. And if you go to the graduate school, depending on what kind of subject, sub-area of electrical engineering you study, sometimes you will confront random field with uncertainty. You want to describe random field probabilistically to do your research sometimes. Got it? Sometimes random graph, because your network is time varying with some uncertainty. Got it? Anyway, so we will study random vector. This is kind of from 1 to 2. So we have here random variable x. We have here random vector x1, comma, x2. And you can extend it to some length m random vector. And here goes random sequence, random waveform. So now you have x of n, and here n can be any integer. Sometimes random process, usually random process can be discrete time, continuous time, but x of t, and here t can be any real number, something like that. So as I told you, we are not going to thoroughly cover all possible random something that is used to describe uncertainty in electrical signal. We will learn very basic random something like variable, vector, and sequence, and waveform. But still, you will believe that this course teaches too much. And that's true. We are going to cover a lot of topics. Unfortunately, as I told you, this course is now kind of graded down to second year electrical engineering students. And its title is now also have introduction to. So I'm not going to cover very deeply, but I will try to cover all these topics. So sometimes you may feel overwhelmed by the terminologies. We will talk about law of large numbers, central limit theorems. Many of you already know what does that mean vaguely, but we will try to make it more precise. And if we have time, we'll also talk about power spectral densities and other things. Okay, now we have around 15 minutes, and I will talk about how can you succeed in this course, okay? And beyond. That's very important. I still remember when I took this course. So after 2 years of undergraduate program, I decided to do my military service. So I left 1.5 years and came back. And this course was one of the first semester courses when I came back from the military service. And I was very successful actually in this course. And the first years after coming back, success gave me a lot of self-confidence. Hey, my brain is not rotten, it's working, okay? And then I studied harder, and I got higher and higher grade. And suddenly I found that I became a professor. First thing is this one. I found that actually after I came back from the service, I didn't take many courses, more courses than before. Before, usually I took 19 credits, sometimes 21. 7 major courses per semester. Can you believe that? 7, 3 times. That's why I couldn't be successful. And after I came back in the first semester, I just took 15 credits. In the second semester, just 12 credits. And suddenly I found that if I study as long hours as him, taking 7 major courses, and taking just 4, I could spend around twice the hours in each subject. And found that midterm exam score is higher than him. And I was not a genius. I just didn't take much course and spend a lot of time on each subject. So my first advice is that if you are taking 7 courses, including this one, drop this one or other courses, okay? Load balance is one of the most important phrase you have to remember to be successful, not just in this course, but throughout your undergraduate courses. Let me tell you 20-year-old story when I came to postdoc. So many of you were born just before this year, probably 4 years. Oh no, some of you didn't exist. Anyway, so I came to postdoc 2004. And at that time, our department was called 삼초땡 department. So just easy, lovely life, except electronic circuit course, taught by very, very demanding professor. Actually, he's still professor emeritus and office in the 2nd floor of this building. So I found a lot of E students was chair of some club because they had too many leisure time than other department friends. So, for example, Control D, EE students chair. Some other Star Love. Almost every club, the electrical engineering students were serving as chair. Why? Because the department was 참초땡. Okay? And our naive senior professors asked me to teach signal gen systems. At that time, the course was on the 3rd grade. So it's like 1, 2, 3, 1, electronic circuits and signal gen systems. And Professor Park was teaching that to make our department alias 삼초땡. And I started to teach signal gen systems. And after a few years, our department changed its name to 극삼초. They suffered a lot by my torturing. Because usually, as probably you've already read from the syllabus, my midterm and final exams start from 7M and infinity. Actually, not infinity, but as far as the TA tolerates. So 1 year, one student took 13 hours to finish the exam. 13 hours. It's not like, okay, I have the exam, let me sleep 6 hours. Of course, there were some students like that, but he just solved for 13 hours. So you imagine how harsh I was. And then suddenly the department enrollment starts to drop, okay, number of E students. When I came here, it was around 65, minimum 55. And after my teaching signal gen systems, eventually we dropped to around 35 to 45. And professors approached me, stop teaching signal gen systems. So I said that, no, I can't do that. Are you going to teach? Everybody said no. So I proposed to shift down this signal gen systems course to 2nd semester of the 2nd year. And then still this trend continued, only changing our department's alias as 이말 3초. And this trend continued. 1 year, only 20 students graduate. Almost every male students just enlisted themselves to the military service, something like that. So what happened? Eventually, I was kicked out because one of the professors wanted to teach to save our department. And then what happened? I started to teach probability courses. Got it? So now, are you prepared? Anyway, so this is very important. And second one is that short-term GPA is less important than long-term growth. So you may have grade lower than what you expected. But as far as you learned something and you can do something better than you are right now, then it's okay. This is actually very important. Some students just stick to their GPA and even the score on the exams. But just think about same knowledge you gained, but some professor gives you very, very, very difficult problems. Then your score will be lower than you expected. That does not mean you didn't learn. Got it? But your perception is, of course, is very bad. So usually these days, I try to give you easy problems mixed with difficult problems to increase the average score. But anyway, remember this one. This is very important. Another one is that, especially for this course, you have to distinguish these two. Definition related to the concept from notation. Let me give you some notation. Many of you have no idea. You know this notation, right? Expectation of a random variable x, probably from the high school math. Hey, come on, I was taught in high school about this notation when I studied 수학의 정석, right? So you all know expectation of random variable x. Now, what is this one? Expectation of random variable x bar random variable y. What is this one? Interestingly, more than half of the graduate students, first-year graduate students, even after they've taken graduate level probability and random processes, fails to answer correctly. You need to know the definition. You need to get familiarized with notations. Otherwise, after 1 or 2 weeks of the spring semester, you will forget almost everything. So never forget. Focus on these two things. Do I really know the definition of something? And am I good at using these notations? Got it? And another one is this one. I myself draws a lot, try to visualize many things. And I also ask you to visualize as much as possible. This visualization helps you a lot when you want to clearly think about something. Even though I emphasize this visualization and also simplification, for a long time, students just ignored my advice. But one of your graduates who has, so this is '11 2011 class, sent me an email one day. And he said that my advice, try to visualize and simplify, helped him a lot when he joined the Samsung Semiconductor. He just graduated our undergraduate program without going to the graduate school. Luckily, joined the Samsung Semiconductor. And suddenly, he sent me an email asking, can I just put your name? So I said, it's okay. So what's the content? And he talked about these two words. Now he is selected as so-called S급 인재 from Samsung Electronics. And now he's doing his PhD course at the University of Michigan, supported by Samsung. So you read it. He talks about how he could be successful by familiarizing these two things, visualization and simplification. Got it? And I have around 30 seconds with a lot to talk. And this simplification itself, probably you already know Albert Einstein emphasized that one, right? And also, some of you know that the father of information theory, Claude Shannon, also Claude Shannon, the father of information theory, also emphasized simplification until you solve the problem, and then try to generalize to get the original answer, something. And now we have over 30 seconds. I will talk about this rest of the things throughout the course by emphasizing the importance of these things. Anyway, so this is the first class meeting. And as I sent you emails, I will try to upload this one, but it's not guaranteed. Sometimes we have technical problem. Voice is totally not recorded. Sometimes battery is gone. So don't rely on this recorded class meeting. Let me finish with this one. Read the syllabus and come to me. Not just Wednesday, right now. Got it? If you have any question. That's all for today.